Good evening, everyone. This is Celso Batalha, Evergreen Valley College, Astro 10. And this week we are focusing on telescopes and light and the nature of light and the types of instruments used by astronomers to gather information about the universe. And that comes, before I start with the lecture itself and highlighting some main points, I would like to set out and the seeds for this week discussion. So, what's the main point of taking a science class or a science course like Astro 10 is to basically to understand how this scientific method work. And scientific method is pretty much developed after the 1700 um, 16, 1700, especially with the work of Galileo Galilei, and after that, in which he was, by the first time, was one that brought experimentation into the process of finding out how nature works. Certainly, there was technology being developed in olden days. So you go 3,000 or 5,000 years ago in ancient Mesopotamia, you did have a very sophisticated technology supporting the life of communities in these mega cities. Um, but you can also claim that the ancient Greek philosophers they did science, and in fact they were responsible for bringing mathematics to science. Especially astronomy was fundamental in bringing these the use of mathematics, especially through Ptolemy. If you recall, Ptolemy was the first one who brought mathematics as a tool to predict planets' positions in the future, because in those days astrology was an important subject in people's lives, and to know where the planet's position would be months or years in the future was very important to make predictions as they thought. And so mathematics came in a way to rescue the astrologers in those days and help them to make predictions. Now, in all of that, although mathematics was being used, although some sophistication was in place in building observatories and sites to do astronomical observations, uh, some might claim that that was not a real science as we do today. Why is that? Well, nowadays, when you do science, you have to observe nature as they did in the past. You have to establish ideas to explain how nature works, which we call hypothesis. So, why is exactly this type of phenomenon working? So you can formulate your hypothesis like they did probably in the past. Um, but there is a difference now. Since the 1600, any hypothesis you formulate, you have to test it. You have to have the ability of negate your hypothesis. And this urgency didn't exist in the past. I'll give an example. I could say, well, the sun is rising in the east and setting in the west. Why is that? And then I could create a hypothesis. Well, God Apollo, God Apollo, which is the sun god, takes his chariot and go across the sky during daytime because he needs to give out warmth and heat to everybody else so we could be alive. And and then he gets so tired that he goes down and rests during the night. And he wakes up again the next day and he keeps completing this cycle. So that was a hypothesis. I could create a religion based on that. Now, the question is, can I test this hypothesis? Can I summon God Apollo and his chariot to my laboratory and scrutinize and verify what's the mass of this god, and what in how if the sky has a certain dimension, can he cover the sky um, with the vehicle he has? I mean, nowadays you to do science, you have to negate, you have to check your hypothesis, you have to create labs, and so that you can bring or part of the object you're studying, or you can create models in the lab that can reproduce the conditions of nature, and by doing so you control parameters and factors that might be responsible um, for running um, or to to govern the experiment you are basically observing. So that's what we do today. So basically, in science, you have a you have observations as we did in the past. You formulate hypotheses to explain how things work. That's true. But you also, in addition to that, you have to be able to check your hypothesis, to validate it, and basically to be able to negate it. And that's the point of discussion now. So for this week, I would like you to discuss the following subject. Well, if astronomy is scientific, and you guys keep talking about quasars and galaxies and things that are so far away that certainly we won't be able to visit them, and some of these entities are even dead, like we might be collecting light of stars that no longer exist because they are so far away and by now they are gone. Or when we observe quasars, they are active galaxies in the past, and by now, if you could instantaneously travel to these places, they are pretty much inactive as our own galaxy in a way. So, how can you say what you say if you haven't been there, if you haven't brought to your laboratory, to your observatory, any part of the materials you are studying? So in our universe, basically you can say that in our laboratory, what we have is pieces of moon rocks, perhaps parts of Martian materials, probably water from early in our solar system, um, probably some organic material that exists in the interstellar medium next to the nebula that gave rise to our solar system, but we haven't gone to any stars out there. So how can you say what you say? So how can you claim that astronomy is scientific if we haven't touched several of the subjects that we use to study? That's the point. Now, probably in your discourse, as you um, report on this seed, I would like you to dive into two major techniques that are studied this week. One is photometry, and the other one is spectroscopy. How these two techniques that astronomers use can help us to say what we say about celestial objects. So exactly what photometry does and exactly what spectroscopy does, and and how these two techniques can help us to investigate celestial objects without going there, and and are they scientific? So that's the main point. Okay, so let me show you briefly the PowerPoints that we have for this week. Chapter 5 and Chapter 6. Chapter 5, it covers the subject of light, basically. So let me go briefly here. Now, light is a phenomenon that carries energy. And this picture here is showing these waves, which suggests that light can be interpreted as a wave-like phenomenon, and that's the first interpretation we have of light. And see these the distance between the bright part in this wave, that is called wavelength, or the distance between the peak of these waves, which pretty much seems to be the same, is also called wavelength. So light, depending on the type of instruments we have, can behave like a wave. And as such, it has a wavelength, it might have a frequency. And what is interesting about light that way is that it travels with the same speed no matter which frequency you are considering. So there you go. So the distance between crests is called wavelength. And the distance between trough points, which is the same here, is also a wavelength, is also called wavelength. Now, because we know how light behave in the laboratory, because you can go to the laboratory in room SA115 and you can easily create an experiment that proves that light intensity diminish with the square of distances, which means you have a light source like a star, and for some reason I don't have my pointer anymore. It's gone. My computer might be with some problem here. Apologize for that. I can't bring the cursor here for some reason. But the bright source is supposed to be a star, and each one of these rays coming out of the star spend like in a way that if you can, no matter how the number one area, the area associated with the number one, which is the first sphere, when you go to the sphere number two, that is supposedly to be twice as distance as it is the sphere number one. So one interesting aspect is that the area encompassed by these rays in sphere number two is 4 times as big as the other one. See that? And when you go to sphere number 3, there is 3 times as far as number 1. The number of equivalent area is 9 times as big as the first one. In other words, if you think about energy, the ability of doing things, the amount of energy contained in a beam of light, so the energy is being spread out in bigger areas as you move away from the source. It's like if you have a pizza and you have certain amount of pepperonis to put on pizza. So in sphere number 1, you can put only 1 pepperoni, right? But in sphere number 2, you have to take that pepperoni and divide in 4 so that you can spread over your pizza. And in sphere number 3, you have to take that single pepperoni and divide in 9 parts equal so that we can spread all over the place, which means consistently each element of the area, think about a slice of a pizza, as you move away from the source, receives less and less pepperoni as you move it away. In other words, the intensity of light falls as you move away from the source. This is such a robust property of light because later on we are going to see that if you happen to know exactly how much energy a source is able to put out in the space, you can, in case you identify a source that is identical to the one you know, the energy of the source that you're observing very far away is being diluted and is spread out as you move away from that source, which means if you observe it with telescopes, you can establish distances. So the inverse square law is a very robust aspect of light. Another thing, our atmosphere functions like a filter that subtract certain wavelengths and allow others to go. So if you look at this picture here, light as a wave-like phenomenon can be then separated in different frequencies, and the aspect of light that has the most energetic and the highest possible frequency is the one associated with gamma rays. So gamma rays followed by X-rays cannot be found abundantly here on Earth. You can find it naturally here on Earth because to provide that energy, you must look for gas that are subject to very high temperature. And we don't have this type of gas naturally occurring here on Earth. Now, if you go to the sun's surface, the gas naturally occurring is the one responsible for providing this rainbow of colors coming out of this little dome that you can see there. So the sun is very efficiently in producing that type of radiation, that type of electromagnetic radiation. And our atmosphere responds nicely to that by opening a window that allows that radiation to go through. And so that's why we call visible light, because we can see it. But the infrared, for instance, has big gaps here. See that? The infrared has a big gap where the airplane is, and I don't have a pointer here. So the atmosphere subtract that radiation in the microwave and far infrared and doesn't go through. And ultraviolet and X-rays, as you can see, and gamma rays too, is also subtract and do not hit Earth, which is good. This radiation is very energetic, and life would suffer a bit if the atmosphere didn't provide protection for it. And as you go to longer wavelengths, you see that radiation doesn't go through the atmosphere either. Now, the window that allow astronomers to have ground-based telescopes, and telescopes are important for observations because telescopes are the tools that allow astronomers to collect light, and light is information. Remember, in the discussion I would like to have with you guys this week, so we don't go to the sources, we don't go to quasars, we don't visit galaxies. There are hundreds of millions of light years away. We don't visit them, we don't need it, because the light these objects are sending out are collected by our telescopes, and we know how light behaves and how light interacts with matter. And by knowing how this interaction takes place and what type of features results from the interaction, we can then predict the environmental conditions where that interaction occur. So if you look in this picture here, the visible window and the radio windows allows astronomers to provide and to create instruments to detect light. Now, in other windows, those there you see the holes, we have to go out to space. So space technology, space telescopes are built with the intent of collecting this type of radiation. Now, the Wien's law, which is given here, a very important law, and that is the one that relates the peak of or the maximum intensity of a given radiation and how that related to the color or to the wavelength or to the frequency that is observed. Stars, they behave with this type of distribution of intensity. That's called black body. So if you observe a star with all possible colors, like if you develop a detector that can count how much energy in each color band you receive from a given source, you might be able to prove that stars pretty much behave with this type of distributions called black body. And it was found a very tight correlation between the peak emission that you can see in this dot that goes to the top of these curves, the peak emission by the wavelength. Now, what light is? The optical light can be separated in different color bands. You can use prism for that. You can use um, grading for that. There are several ways of creating this rainbow. But the main point is astronomers can then um, use this technology to create rainbows. And what was found in the 1800s is that if you look with very good detail in this rainbow, you find what's called absorption lines, which you can see in this picture. So these traces in dark are caused by atoms that happen to be in a gas. So if you have a gas and light is propagating through this gas, so atoms in this gas will absorb light in very specific frequencies. And and by doing so, the interaction of atoms with light produce specific signatures like the one you're seeing here that allow astronomers not only to identify what type of atoms the gas um, carry, but also the abundance of gas, the temperature of the gas, the conditions of the gas that promotes these absorptions. Now, there are other type of gas-light interaction that produce not absorption, not a depletion in the rainbow, but specific emissions. It's called emission lines, and that's what you are seeing here. So you have a no background at all, but you have some emission lines. Now, atoms, and I mentioned the word atoms, exactly what atoms are. Atoms are the building blocks of our material world. So atoms are responsible for making up the room I am, the room you are, but also our bodies. Our bodies are made of atoms, and what we learn, and that was part of a previous discussion we had in cosmology, the hydrogen and helium, perhaps some lithium and beryllium were created um, during the first few seconds or minutes of the Big Bang. And then after that, stars came in, and when the stars were formed, then the other atoms we know were formed too. So helium, beryllium, perhaps some lithium were formed in the Big Bang, and all the other atoms were formed in stars. So the stuff that you see around you, the primary stuff you see around you, all the metals, the carbon, the neon, all of that came, the nitrogen that we breathe comes in our system. We don't use the nitrogen, the plants do a lot. They all came from dead stars that no longer exist. But so atoms are made of protons, positively charged particles in the nucleus, and electrons that go about. So the interaction of light um, with atoms is done by a very simple approach is given in this diagram here. So each circle represents energy levels where electrons are more likely to be found. And when an atom subtracts light from an incoming beam of light, that energy the light itself carries is used to move the electron out to a more energetic orbit. So we say in under these conditions, we say that the atom is excited. And after a very short period of time, then the electron goes back to its own state. And when it does happen, this a photon or a particle of light, if you can use that expression, is expelled from the atom. So you can summarize the interaction of light with matter in the following way. So you have a source of light, and that source of light, if you observe directly to it, you have a continuous spectra, which you see, which is indicated in the rainbow in this picture. But if you have a cloud of gas that could be a stellar atmosphere, could be gas in the interstellar medium, that happen to be between you, observer, and the light source itself. So as the light penetrates and propagates through this cloud of gas, um, specific frequencies, specific colors of this rainbow will be used by the atoms itself to get themselves excited. And then that radiation is depleted. And that's what you see in this, in the right hand side, the continuous spectrum with dark lines. Okay. And so as atoms get excited, um, after a short period of time, they undergo this excitation, and that's what you see as bright line spectra that is shown on the lower end of it. So if you add those two um, figures, the continuous spectrum with dark lines, if you add that to the bright line spectra, if you add those two, you have the original continuous spectra, basically. So this is so much for the light. Which other part I would like you to also read in this week is about telescopes. So, well, what is it? Telescopes are the instruments by which astronomers collect light of celestial objects. And as we saw in the previous series of slides, um, some telescopes are put out in the space because we need to collect light or specific light without that wouldn't go through the atmosphere. But also, even if you want to observe in the optical range, like a Hubble telescope, which is a space telescope, going above the atmosphere has the advantage of avoiding what's called scintillation or turbulence in the atmosphere. So let's go through this chapter. Now, observatories existed in the past, but not with the use of telescopes. So Stonehenge was one that started to be built about 3000 BC and stopped being modified by 100 or 200 BC, and has gone through several phases. Stonehenge. Um, in the left-hand side, you can see Machu Picchu in Peru. But exactly, modern astronomers use primarily telescopes, and we don't do positioning or astrometric so astrometry so much like it was used to do in the past. So there are two types of telescopes, and this is important. This you must know. There are two types of telescopes. One is the so-called reflectors. Think about reflection, think about mirrors. So reflectors use mirrors in order to collect light from celestial objects. The other type of telescopes are called refractors. Refractors use lenses to collect light and bring them to what we call focal point, as you can see right here. So those are the two configurations. The one to the left is a refractor that has a lens in the very opening of the telescope, and the second to the right, the second telescope to the right is a reflectors that use mirrors to collect light and bring the light to the focal point. Now, the bigger the mirror, the more information you can collect. Remember, telescopes, what they do, they collect light, and light is information. and bring to the focal point so astronomers can take that information and stream to the computer and analyze using the knowledge they developed in their studies. Now, the bigger the telescope, the bigger the aperture, more information can be collected. And that was one of the disadvantage of refractors. Why is that? Well, refractors, let me see one example of a refractor here. There you go. A refractor is a telescope that uses lenses. So this is a refractor. One of the old type of telescopes is 1 meter lens that happen to be on the very top of the telescope. The problem with the refractors, there are several, but one is if you want to increase the size of the lens, besides being very, very technologically challenging, the telescope has to be big as well. Because remember, in a refractor, like here in the left-hand side, the light has to be funneled to the focal length. So if you have a large lens, you have to have also a large um, telescope for that. Now the reflector, as you can see here, you can do tricks. You can put mirrors inside and diverge the light to different positions in such a way that you can play around um, with with the focal length, as you can see in these configurations here. You can converge the mirror to a point that you don't need a big of a building to host the telescope. A second disadvantage of refractors is since you have lenses, problems such as chromatic aberration, which is the fact that a piece of glass will bend light of different colors in a different way. It bends less in the red than it does in the blue. So when the white light goes through the lens itself, it spreads out, and you see a kind of a rainbowish image of your source, and you don't want that. So you have to do corrections, chromatic corrections to that, and which means you have to not only have the lens, but you have to make the correction, and that is too costly. And the third disadvantage is mirrors, and in fact, glasses are fluid. And if you build big lenses, besides having big, you have to have a big buildings for it. The lens itself deforms like a big blob, right? And the image is going to be deformed too. Um, like ice. Ice is a solid thing, but it also can be deformed like glass, and you don't want that to happen. So mirrors have the advantage that you don't need to build, let's say, a 10 meters telescope that has 10 meters or 30 feet diameter. You don't need to have that big of a mirror. So what you do, you create small hexagons and connect them together. And the technology is less challenging, and the efficiency is quite high. So in modern astronomy, as important as it is to have a bigger telescope, you also have to have technology to improve your imaging. And adaptive optics is one of this such a technology. And try not to confuse that with active optics. Um, active, active optics is one that you have a mirror that has actuators that compensates and try to initiate the process of straightening out your images right there in the mirror itself. And adaptive optics is a technology that allows astronomers to eliminate or partially eliminate the effects or turbulence in the atmosphere. And the way it does, um, the mirror receives um, um, in fact, per several instructions over hundreds per second in order to correct itself from turbulences in the atmosphere as um, a star guide or some laser star is observed at the same time. So if you know the source that happened to be outside the atmosphere and you observe that source, as you observe, that information is passed on to the telescope, to the mirror itself, to the primary mirror, and the mirror is corrected so that the initial image is restored. Now, depending on the type of technology or the type of source you want to observe, you choose a different type of technology, not only telescope but also wavelength. And this is an interesting picture because it shows that infrared can go through certain types of sources. In fact, infrared technology is very efficient in observing regions of star formation. And here's a design of a spectrometer, which is one of the tools astronomers use to observe star objects. Pretty much that is what I want to go through. And good night, you all. Let me start taping now.